Now we come to the particle physics example. We have the standard picture of, which is of course not a real picture because it's really showing things underground. It superimposes on the map of the link between France and Switzerland. This actually crosses the border. It has, we have here the initial acceleration is done here. The protons and antiprotons are then injected into these rings, and they're collided at various places. You can see where the rings cross with the protons and antiprotons. 1, 2, 3, 4. And these are the halls where the different experiments. We see CMS Atlas, which are the two general purpose experiments, LHC B and Alice, which are more special purpose and somewhat smaller data sizes. So now we note here that there's 27 kilometers around this ring, and it's actually at the depth of 175 meters at its deepest. So the data is the collisions happen here along at these sites here. There are these huge apparati which are giant by any reasonable standards, which take the data, they record the results of the collisions. That data is written out to disk. It's analyzed by a special large local cluster to select the more interesting events, and those more interesting events go on for detailed analysis. These are huge examples of global science. Namely, CMS, one of the two general purpose experiments. The other is, of course, Atlas. Has 3,600 participants, 183 institutions in 38 countries. Wow, that's. I used to work in this field. We had 30 people in our experiment, and I found that pretty big. And one of the reasons I left that field is I thought working with 30 people was not so easy. But now they have 3,600 people, so obviously I was a bit impetuous in those days. So this now goes a little more detail in the actual analysis. So we have to analyze this data. That's done through one of the major resources is the LHC grid, which has 350,000 cores running and 2 million jobs per day. The LHC analysis is organized into these three tiers, which are basically CERN is sort of tier 0. Tier 1 is sort of in the country. Tier 1 in the US is a Fermilab in Illinois, and there's a tier 1 in 3 other places in Europe, and then lots and lots of tier 2s, and then tier 3 is basically your local workstation. We have around 15 petabytes of data and 200 petabytes, 15 petabytes of data per year, 200 petabytes total. And here's some data about Atlas experiment in 2012, had 8 petabytes of tape, 10 petabytes of tier 1 disk. And I guess actually this slide here about the US tier 1s is not correct. It misses out some. There is a tier 1 also at Brookhaven. And tier 2 centers have 12 petabytes in total. And this is just one experiment, Atlas. CMS has a similar architecture and similar sizes. Notice that this information gain involves not just raw data, it also involves simulations which are used to be able to analyze understand the data analysis and quantify the errors in that analysis. And there's almost an equal amount of data from Monte Carlo, which are the simulations that there are from the real experiment. So it points out here that the accelerators are increasing in power, but the Moore's law is sort of slowed down and has now become core law, not speed law, and so that requires new challenges. And there's also the usual issue of power consumption and so on. I would say that it's not so obvious to me that this field is not as challenged as some other fields because they can just increase the size of the number of cores, and maybe they can even do some quicker pre-analysis to be able to isolate those those events that need the full analysis. And they certainly probably do need to relearn. I mean, the software, the planning for the software for this um, discovery of the Higgs happened 10 years before the actual Higgs was discovered. So this is a huge effort. At every stage, large-scale testing is being done. So, and I think in the future, clouds will turn out to be particularly important because they are naturally supporting this type of application. Whether you can actually afford to do it on commercial clouds, or you really need these sort of 3 cycles from physics clusters, is not so clear. Now we come to use case 40, the high energy physics experiment, BEL 2. This is only involves 400 physicists and engineers. It's in Japan at Tsukuba, and whereas LHC is accelerating protons and antiprotons, this is accelerating positrons and electrons, the antiparticles, of course, of each other. And when E plus and E minus collide, they, among other things, can be run at an energy where they have a very enhanced production of the B meson. The B meson is made from a B quark combined with conventional quarks, U bar and D bar, up and down quarks in the antiparticles. And it has very high intensity because it's very specialized and optimized for this particular. It's nowhere near the total energy of the LHC, but and also because of that, the data analysis is somewhat simpler because fewer particles are produced, but it has to be done highly accurately because they're looking at small effects called CP violation, which is a very subtle effect in the interaction between the particles of high energy physics. So this is currently running the BEL accelerator. This will become BEL 2 with an upgrade. And that starts in 2015 with a factor of 50 increased data. They expect to get 120 petabytes. And actually here we see the Monte Carlo ratio is 100 petabytes to 15 petabytes of physics data. They want to be able to take the data in Japan and basically transfer it continuously to the US. And they have, there in the US, they were using the so-called Open Science Grid, GN4 and Dirac and FDS and BEL 2 are pieces of software. And this has, what is its characteristics is MR-stat, because that's the way when you do physics analysis, you're doing large-scale statistics, histograms, that's MR-stat. Parallel PP, pleasingly parallel processing, that's because each event is processed on its own. Well, Monte Carlo MC, that's the Monte Carlo data. We notice that's 6 times as big as the actual raw data, and the parallelism is over collisions, whether those collisions be real collisions or simulated collisions.